I am happy to share my work on improving human and AI decision-making outcomes through value-aligned interaction. I would first like to clarify what I mean by value-aligned human and AI interaction. Typically, when we speak about value alignment, we focus on the AI. The AI's decisions should be designed to align with the norms and the values of society, such as upholding fairness, privacy, being transparent, and so on. While that should be the goal, and it is a challenging task on its own, I argue that in AI-assisted decision-making, it is not enough. We're missing a key component, the human who is interacting with AI. Instead of focusing on the values of AI in isolation, we need to consider the values that emerge from the human and AI interaction. I posit and will show evidence that by designing an interaction layer that optimizes the values of the decision maker, we may achieve desired human and AI decision-making outcomes. Okay. So AI is everywhere, and decision makers are increasingly making decisions while assisted by an AI, including in critical domains such as healthcare, aviation, but also in seemingly lower stakes, such as, like, for example, coding, writing assistance, and so on. So to clarify the terminology, these settings in which a human operator makes a final call given an AI recommendation are typically referred to as AI-assisted decision-making or human and AI decision-making. So what does AI-assisted decision-making look like in practice? The current paradigm of AI decision support, which I will refer to as simple explainable AI, looks as following. Imagine a clinical setting. For example, given a decision instance like patient features, the AI provides a recommendation of whether that patient has the disease or not. And this recommendation is often accompanied by an explanation where the AI tries to explain its decision with the hope that the human operator will override wrong AI recommendations and accept the correct ones. The explanation that I show here is a feature-based explanation, but you can think all sorts of explanations, including natural language ones that are generated by LLMs or image-based explanations, and so on. So now that we have a joint understanding of the setting, given that humans and AIs have different strengths, it was expected that these human and AI teams would achieve complementary team performance. So, in other words, it was expected that human and AI together would perform better than the humans alone and the AIs alone. Yet, this is not what happened. When assisted by an AI, humans perform better than the human alone, but worse than the AI alone. And this finding has been empirically shown by a series of studies, and it's currently a hot area of investigation. I argue that this mismatch between this expectation of human and AI complementarity and the reality that we're not achieving it is partly due to the misalignment of optimization. So rather than optimizing for the human and AI team performance, we have optimized for the AI's performance in isolation, without considering whether and how the decision maker would make use of it. By hyper-focusing on the AI performance, prior work has mostly overlooked human factors in AI-assisted decision-making. One such critical factor is human cognitive motivation as a construct. Shifting the focus to the decision maker and what they care about, we hypothesized and then with our work demonstrated that cognitive motivation, in fact, moderates the performance of the decision maker when they receive AI assistance. So what do I mean by this? Remember the paradigm of AI decision support, the simple explainable AI paradigm. It is all well in place, but except there's an underlying assumption that people will cognitively engage with the AI's recommendation and explanation and will be able to override wrong decisions and accept the correct ones, which mounting empirical evidence has shown to be false. There is no human and AI complementarity. This lack of cognitive engagement becomes particularly apparent when we disaggregate the performance of the team when the AI gives a correct recommendation versus an incorrect recommendation. Across tasks and settings, we see that people over-rely on the AI. When the AI gives a wrong recommendation, they tend to rely on it, even if they can make a better choice without the AI. And this has been shown also with experts. But why do people over-rely on the AI in the first place? We posit that the dual process theory provides a useful lens through which to understand why people over-rely on the AI and why explanations don't help. Because evaluating every AI suggestion and explanation requires substantial cognitive effort or system two thinking, people develop heuristics and about whether or when to rely on the AI suggestion. And giving them a suggestion provides a shortcut to the decision, which makes the decision-making an easier task. Therefore, we hypothesize that if people can be induced to engage in more analytical thinking when processing AI recommendations and explanations, their over-reliance will decrease. To this end, we devised interaction interventions called cognitive forcing functions that disrupted heuristic thinking by allowing people to form an initial hypothesis before seeing the AI's recommendation and explanation. We experimented with a nutrition-related task as a task accessible to lay people since we ran our studies on crowdsourcing platforms. The three cognitive forcing functions that we experimented with were update, where people in this condition could make a decision on their own first before seeing the AI's recommendation and explanation, or wait, in which people saw an AI is processing an image for 30 seconds before they saw the AI recommendation and explanation. And people really hated this condition. They said that, oh, the AI is broken, like it's so slow and so on. And also on demand, in which people could click on a button to see the AI recommendation and explanation. This was also inspired by curiosity theories, in which if people request the information by themselves, they are more likely to engage with it. Sorry. So our results show that cognitive forcing functions indeed reduced over-reliance, or in other words, when people interacted with cognitive forcing functions, their performance on instances when the AI was incorrect was significantly better than people that interacted with the simple explainable AI paradigm. But this over-reliance, this reduction in over-reliance came at a cost. People did not like the interventions that made them engage more analytically with the information. So essentially, there was a significant negative correlation between the self-reported acceptability of the interface and people's performance when the AI was incorrect. Coming back to the bigger picture, our cognitive forcing functions intervened in the cognitive motivation by forcing people to engage with the AI recommendation and in turn improved performance on instances where the AI suggested a wrong recommendation. Together with another study of ours, our work strongly suggests that decision makers' cognitive motivation to engage with AI assistance is critical for people to evaluate and appropriately incorporate AI advice into their decision making. Yet, as a field, we're not considering cognitive motivation when we design AI for decision support. Therefore, given that human motivation is critical, I strongly believe that a path forward in AI-assisted decision-making is to design for and optimize the intrinsic motivation of the decision maker so that they are intrinsically motivated and they are excited to engage with the task and the tool that is providing them support. But what would it mean to optimize for decision makers' motivation? Social science theories, including the seminal self-determination theory, posit that humans are intrinsically motivated when their needs and values are met in the workplace. To name a few, people value growth and improvement. They generally want to get better at their jobs and improve over time. They want to have agency in their work, make fair decisions, and feel a sense of belonging. Okay, this cough came at an inappropriate time. Okay, therefore, I hypothesize that focusing on and optimizing decision makers' values will lead to improved well-being, increased motivation, and in turn, improved performance in the decision making. So let's zoom in on growth and improvement. How would we optimize people's growth and improvement along with their accuracy in AI-assisted decision-making? Recent work shows some worrisome results. In other words, the current decision paradigm where we provide people with AI recommendations and explanations actually exacerbates people's learning. So essentially, when people are provided with AI recommendations, they more likely do not engage with those recommendations. Therefore, they do not learn about the domain and the task, which is worrisome because it hinders the growth of decision makers and may even lead to de-skilling of them in the workplace. So in a recent project that will be out soon on arXiv, we asked, does the current paradigm of support offer the best support to all people in all contexts? We argue that it does not. The different objectives may require different assistance. For example, if we try to optimize people's skill acquisition about the task, we may choose not to show them recommendation, but show them only AI explanations that will give them more information about the decision instance, but not provide them with the answer. Therefore, they are more likely to engage cognitively with the information and learn something about the task while reaching a decision. Different contexts may require also different AI assistance. For example, when the AI is uncertain, we may choose to withhold the support so that a person is allowed to make their decision on their own. And different individuals may require different AI assistance. One important individual difference in AI-assisted decision-making is individuals' cognitive motivation to think. The need for cognition in psychology is a personality variable that reflects the extent to which individuals are inclined towards effortful cognitive activities, which previous work has also shown to have an impact on how much people engage with the AI support. To optimize these human-centric objectives, such as human and AI team performance, but also human growth, then how do we decide which kind of assistance is best for whom and when? To this end, we cast the problem of human and AI decision-making as a Markov decision process and posit that reinforcement learning provides a useful framework to optimize human-centric objectives through interaction. In other words, we seek to learn what type of AI assistance to provide to people given the objective and the context. Our proposed approach is generalizable, but we here instantiate it with two different objectives, the immediate decision accuracy and also long-term human learning. We construct the state space and action space according to these objectives. The state space consists of people's need for cognition, their skill on the task, their skill on the concept. You can think of the concept like, for example, integration or derivation if this is a math question, and the concept in question and the AI's uncertainty about the advice. Whereas the action space is comprised of simple explainable AI, which might be useful if the answer is correct and we seek to promote reliance, showing people explanation only, which may be useful if we seek to improve learning, showing people explanation and recommendation on demand, or like providing them with no assistance. So to give you a flavor of the decision-making task that we experimented with, here is a sample of the series of exercise prescriptions tasks that crowds were prompted to complete. To construct these vignettes and the representation of the exercise space, we teamed up with a professor of kinesiology, And the vignettes look something like this, where that Daniel wants to increase flexibility and lose weight. He is 31 years old and works as a cook. His current engagement in physical activity is low. He is obese. He enjoys individual and indoor activities. He has also access to a gym. And based on these descriptions, people then had to pick one of the sets. And the AI recommendation and explanation, so the AI recommendation and explanation looked as following, where the AI pointed to the correct decision and then also gave an underlying explanation why it thought that that was the correct decision. So we followed an offline reinforcement learning approach, which involves 3 steps. First, it's collecting data with an exploratory policy, then learning the optimal policies for different objectives, and finally evaluating the optimal policies with human studies. So for the data collection study, we treated each participant as an episode. They were presented with a series of questions in which AI assistance was sampled uniformly. There were also task blocks in which people received no assistance and which served to measure people's learning about the task. Given these interaction data, we then learned policies while optimizing human learning and accuracy as objectives with Q learning. We inspected the learned policies. The graph here displays the distributions of actions over the state space for the 2 objectives and the 2 NFC groups. I want you to focus on the lower quadrant on the right, where the objective is learning and the group is low in need for cognition. To optimize learning, the policy has learned to primarily show people low in NFC with explanations only. Because if they, in addition, receive recommendations, they may rely on it without engaging cognitively and hence no learning. But for people high in NFC, who are motivated to think, even when presented with recommendations, they would still learn about the domain. Now, let's look at the accuracy as the objective. Let's zoom in, and this is the policy optimized for accuracy only, as it becomes particularly interesting when we split the graph by the underlying AI's uncertainty or accuracy. When the AI is accurate or like certain, for both groups, simple explainable AI and explanation only were picked as the top actions. But when the AI is incorrect, for people high in NFC, showing them no assistance and allowing them to make the decision was seen as the top actions. Whereas for people low in NFC, also providing them with on-demand support was seen as equally good action. To me, this was surprising because showing no assistance made more sense as an action. Therefore, I went into the data and explored why this happened. And what I understood was that people low in NFC, when they are provided with the on-demand action, they are not even motivated to click on the button and see the AI support. So essentially, by inspecting the policies, we learned something about the decision-making space. Specifically, we learned that people low in NFC are less likely to click on-demand as an intervention, and AI-assisted decision-making. Once we learned the policies, then we ran 2 evaluation studies with different batches of people to understand how successful they are in optimizing these different objectives. So similarly to the data collection study, people interacted with made a series of decisions while they had these pre and post task blocks with no AI assistance. And during the intervention phase, they were interacting with one of the optimal policies or baselines. So I'm happy to chat about this in the Q&A, about the implementation details and the hyperparameters, but I will be brief here. In the first experiment, we randomized participants into 3 conditions. They either interacted with the accuracy policy, the learning policy, or the simple explainable AI as a baseline. Here are our results. The dashed line here indicates the AI alone performance. Let's look at the x-axis first, which shows participants' accuracy with different policies. We can see that policies that optimize accuracy indeed improved participants' accuracy, with people high in NFC surpassing AI alone performance, therefore reaching human and AI complementarity. Looking at learning, for people high in NFC, we see that regardless of policy, they learn similarly, which is in line with our understanding that these people like to engage with information. Whereas for people low in NFC, they learn significantly more with the learning policy than with the accuracy policy. These results show that different policies, which in this case, the accuracy policy and for people high in NFC and the learning policy for people low in NFC, were successful across objectives for different groups of people. And what's more is that the subjective ratings also showed that people preferred these policies that they learned more and performed better with. To investigate our approach more deeply, we ran a second experiment with more conditions, including a combined policy in which we optimized for both accuracy and learning, and also other baselines, such as a random baseline where we sampled the action randomly, and an explanation-only baseline where we showed people with explanations only. Looking at the accuracy as the objective, our results show that policies optimized for accuracy. Now are both the accuracy policy and the combined policy improved people's accuracy more than the rest of the policies, with people low in NFC, in this case, achieving human and AI complementarity. Learning, however, was not significantly different across policies, except that people low in NFC learned significantly more with the explanation-only condition compared to the simple explainable AI condition. So we believe that this may be because of two reasons. First, learning is a far weaker and noisier signal than the accuracy, thus more difficult to optimize. Additionally, the results of the second experiment may have been influenced by our modified experiment design. Compared to the first experiment, in the second experiment, we increased the number of test questions with the hope of strengthening the learning signal. However, because we did so, we also reduced the number of intervention questions, thereby inadvertently limiting participants' exposure to different concepts and their opportunity to learn. So to summarize, we highlight the importance of designing AI decision support that optimizes human-centric objectives beyond accuracy. We proposed and demonstrated offline reinforcement learning as a promising approach for modeling human and AI decision-making, for both optimizing different objectives through interaction, but also for enabling discovery in the human and AI decision-making space. We also identify a novel research challenge for designing AI support, explanations, and interaction paradigms that optimize human learning about the task, along with their accuracy in decision-making. So to bring it all together, to improve the quality of life and well-being of decision makers, I argue that we should shift the focus towards their values and build AI tools that optimize for those values. This, in turn, will increase their intrinsic motivation, will improve their well-being, and will also result into more engagement with the tool and the task, which our work has demonstrated to be a moderator of the performance of human and AI team. I also presented offline reinforcement learning as a novel approach with the promise to achieve such value alignment through interaction. While in this presentation, I focused on the values of the decision maker, human and AI decisions affect other stakeholders as well. In another thread of my work, we show that different groups of people prioritize values differently. And we built AHA, an LLM-powered tool to help decision makers uncover the values of other stakeholders by generating examples of harms that can happen by deploying different AI systems.